Hello viewers, welcome back to this course. So today we are going to start with the next lecture, that is 11th lecture. So in the last lecture we have started with the green functions, that how the green functions are helpful for finding out the particular solution for a given differential equation. So today we will discuss the another topic related to the differential equation, and that is the adjoint operator. And then we will discuss that how the differential equation, any operator, a differential operator and its adjoint operator, and then we find the relation between the green function of the linear operator and the green function of the corresponding adjoint operator. So today, we will start with a new topic, so that is called adjoint operator. So before this one, we can start with the matrix theory. Like in the matrix, so suppose I have a matrix that is of dimension n cross n, and I have two vectors, that is x and y, that also belongs to Rn. Then I define my x transpose A y. So this is my matrix, I post multiply by y and the pre multiply by x transpose. And suppose if this is equal to y transpose some matrix B x. So this is true. If you see here that the role of x and y has been interchanged. So here x transpose A y and becomes y transpose B x. Then from here, if this is possible for all x and y, then we say that B is A transpose. How it is happening? Like I have a x transpose A y, I am taking the transpose of this one. So I will apply the formula of the transpose. So it will be y transpose A transpose x transpose transpose, and this I can write as y transpose A transpose, and this will be x. So in this case, and now this becomes, so it is given that this is equal to y transpose B x. So from here I can say that my B will be A transpose. So in that case, this is called transpose of the matrix A or we also call it transpose operator of A, because we know that the matrix can be written as a linear transformations in the, and then it is can be written as a operator, because these things we have already discussed in the course of linear algebra. Now the same thing, so I want to apply for the linear operator, because here we are dealing with the matrices only, then we are able to do this multiplication. But what will happen if I go by the linear differential operator and then I want to apply the same methodology to find out the adjoint operator? So this is called the transpose of the matrix or transpose operator of the matrix. Now, so before that one, I will introduce another concept that is called the inner product. Because inner product is that, suppose as we know that if I have two vectors, like I take a matrix vector x, so I just take vector 1, 2, 3. So this is my vector, and I take another vector, so that is just take 0, 1, 1 and all belongs to R3. And if I want to multiply these two vectors, then I have to take the dot product. So this dot product will be, in this case it will be y. So, you can say that this will be 1, 2, 3 and this vector be. So, in this case actually this vector we generally take the column vector. So, I will change this one to in this form. So, suppose this is the vector 1, 2, 3. So, we will take the vector as a column vector. Another vector I am just taking 0, 1, 1 and then I want to define this x transpose y. So, just let us see what will happen. So, x transpose will be 1, 2, 3, it becomes the row vector and then it is the column vector. So, if I multiply these two vectors, it will be 1 into 0 plus 2 into 1 plus 3 into. So, this is the multiplication and then from here I will get the 5. So, this is the output of when I multiply the or I take the dot product of the two vectors. So, this is called dot product. Now, what will happen if I instead of this vector I have two functions. Suppose I have one function f1x. So, that is equal to I said just take x square and I take another function f2x as sin x, because I already know that these functions, these are the continuous function and they also make the vector space. Generally we call that vector space x and we call it the L2 space, and let this vectors these functions are defined in the interval. So, that interval I just take a b. So, this is the space of functions such that the L2 space means so that if I take the integration of square dx, then it should be finite value. So, this is so all the continuous function we were discussing for solving the differential equation, that also belongs to this space. So, in this space, so this is a vector space L2 space. Now, what will happen if I want to multiply or the two vectors? Suppose I want to multiply, what will be the answer of this f1x into f2x? So, in that case we just extend the idea of the dot product and then we define the inner product. So, let us define inner product. So, this is the definition. So, let that V be a real vector space over a field F, then a real inner product on V is a real valued function that associates each pair of functions, each pairs of vectors. So, I call it x and y. So, this x and y belongs to this vector space V, a real number. So, that we represent by this sign, that satisfies the following properties. So, what is the first property? The first property is that if I take the inner product of x and y, then it is same as taking the inner product of yx. So, this is true for all x and y belongs to V. It means I can just interchange the x and y. So, it should be true for this case. And the second one is that for kxy, I can take the common k common, then it should be equal to xy. So, it should be also true for x and y belongs to V and k is a scalar. So, in this case we are taking the real numbers. Now, so this is a scalar. Third property is that if I have summation of two vectors and I am taking the inner product with the z, then I should be able to get x z y z. So, this should be true for all x y z belongs to V. And the fourth one is that if I take the inner product of a vector with itself, and this is always greater than equal to 0, and if is equal to 0, that will implies that x equal to 0, because I know that if I take the dot product of vector with that cell with itself, then it gives the length of the vector. So, in this case if the length of the vector is equal to 0, it means the vector itself is 0. Whenever we are dealing with the functions, in that case, so the inner product in this case becomes, so now let us suppose that I am taking V as a L2 space, then in this case if I want to take the inner product of two functions, so suppose f1 and f2 belongs to V, then I want to define the inner product of f1 and f2, then this will become the integration from a to b f1x f2x dx. So, that will be the inner product in that case whenever you are dealing with the functions. So, like suppose I have a two function, as we have taken that f1 is x square and f2 is sin x, and these two belongs to my L to AB. So, in this case, and if I want to define what will be the inner product of f1 f2, then it will be from a to b x square into sin x dx. So, this will be the inner product of the two function in L2 space. Now, so with the help of this one, now I will define what do you mean by the adjoint operator. So, we already know that in the previous classes we were dealing with the second order differential equation of this type. So, this is a1x y dash a2x y is equal to 0, and in this case we know that this a0 a1 a2 all are continuous in the given interval x belongs to AB. So, if they are continuous in the interval, it means they are belonging to the L2 space, and y is the solution, that yx is the solution and its second derivative is also there. So, it means that yx itself is also a continuous function. So, that yx the solution also belongs to the same space, that is L2 space. So, from here I can define the operator Ly as a0 x d square by dx square plus a1x d by dx plus a2x yx. So, this is my operator I am taking. So, this is my differential operator. I call it linear differential operator, and this is my differential equation and this is my differential operator. Now, what I want to do, I want to find out what will be the adjoint operator for this linear differential operator. So, that one I want to find out. As we have found that whenever I was taking the matrix, we can find out the transpose of matrix, and we have seen that the transpose of matrix in that case is called the transpose operator, or we can also call that as the adjoint operator. In the matrix theory, we know that the adjoint of the matrix is a different concept. So, that is why in the form of the matrices we always say that the transpose operator. So, let us find out that how I can find the adjoint operator for the given differential operator. So, for this one, so this I take as a 1. So, this is my differential equation. So, this is my operator, and let this differential equation has boundary or initial condition. So, I just take the boundary condition as u x is equal to, so this is equal to 0, and x at, suppose I take x at alpha is equal to 0, and u at x equal to beta is equal to 0. But in this case we are taking this, so I just take here I should, because I am taking a here, so I should define here alpha beta. So, I define the boundary condition that u at x equal to alpha is 0 and u at x equal to beta is 0. So, this is the I am taking as a homogeneous boundary condition. So, in that case if I take B as the operator, boundary operator, so I can say that B of u is 0. So, then this B is called boundary operator. So, now I have, so this is my boundary operator, I call it 2. Now, so based in this one I want to define, so I just choose let I take a function Vx is another function belongs to that same space, vector space V, from where that y is there, a naught is there, and has every characteristics of u of y. So, in this case actually this y is a function of x and v is another function I am choosing. So, instead of y I just take, just because here we are dealing with two type of function. So, I instead of y I just define my function as u, because in that case it will be easy to define. So, this is also u. Then my u is this one, and so I take that Vx is another function defined and it has every of ux. It means that Vx is another function and it has the same characteristics as of the ux. Then I define the inner product. So, let us define the inner product. So, inner product I defined as V, that Vx we are taking with Lux. So, just short I will call it, because these are the functions. So, instead of this one I just write this is V Lu, and I just told you that in this case the inner product will be from alpha to beta. So, V is a function I am taking. So, I am defining that Vx, and then I am defining Lux dx. So, this is my inner product of the two functions. So, from here I can define that this will be alpha beta Vx, and then L I am just this one. So, this will be A0. So, from here I can write A0, it is a function of x, and then I can say u double dash plus A1 u dash plus A2 u, and then taking the integration with respect to x. Then I can solve this one, and this becomes alpha beta, then we multiply this Vx taking inside. So, I will call it Vx A naught u double dash dx plus alpha to beta, I am taking the integration. So, it will be Vx A1 u dash dx plus alpha beta Vx A2 u dx. So, this one we are defining. So, this is all function of x. So, from here then what I do is that I want to solve the first integral. So, in this case if you see I will apply the product rule. So, now what I do is that I will choose this one as a first function and this one as a second function. Similarly, this one as a first function and this as a second function. This first and this is second, but this will be. So, let us do this one. Now, from here if I take the integration, so this I will take as a v, just I am putting v A naught, the integration of u double dash, so it will be u dash, putting the limit alpha beta minus alpha beta and taking the derivative of v A naught and then u dash dx. So, this will be the result for this integral, plus the same thing I will do here. So, I will take it v A1 and then u. So, I am taking from alpha to beta minus alpha beta. Now, I am applying the same integral of this one. So, it will be v A1 u alpha, taking the limit alpha beta minus the derivative of v A1 dash u dx and keeping this integral alpha to beta as same. So, this is a v A2 u dx. Now, from here I will keep this quantity here. So, it will be A naught v u dash plus A1 v u. So, this quantity I will separate this one. Then this is the integral and I again want to solve this integral. So, this integral if you want to solve, then again I will apply the product rule. So, in that case it will be v A naught dash u. So, this will be from alpha to beta minus alpha beta and taking the double derivative of this one. So, it will be the double derivative of this one and then u dx. So, this will be there, then minus and then applying the same thing here. So, it will be again v A1 dash. So, this will be remaining the same way. So, here there no need to, just keeping the same thing here. Then it will be minus v A1 dash u dx plus alpha beta v a to u dx. Now, if I want to solve this one further, then so from here so then what I will do is that, so I want to solve this one. So, this factor is again I can separate. So, it will be a0 v u dash plus a1 v u minus v a naught dash u. So, this one I just take alpha beta minus. So, now I want to keep this one alpha beta. So, what I need to do now is that I have to take the second derivative, two derivative of this one. So, if you see from here I just write down that the v a naught dash, so that will be v dash a naught plus v a naught dash, and if I just take the two derivative of this one, so v a naught double dash, so this will be v dash double dash a naught plus v dash a naught dash plus v dash a naught dash plus v a naught double dash. So, from here I can write that this will be equal to v double dash a naught plus 2 times v dash a dash plus v a naught double dash u dx minus alpha beta. So, it will be v dash a1 plus v a1 dash u dx, and then plus alpha beta v a to u dx. So, this is the quantity I will get. Now, if I further solve this one, so I will get the quantity. So, this quantity will be now v a naught u dash plus a1 v u minus. So, this quantity I will find out. So, this is a v dash a naught plus v a naught dash u alpha beta plus, and this quantity will become alpha beta. So, a naught, I am taking a naught v double dash plus 2 times a naught dash v dash. So, this is the that quantity plus a naught double dash v minus a1 v1 v dash minus a1 dash v plus a2 v. So, this quantity can be written as this one. So, I am just taking the terms together. So, this is this one I have taken 2 times of this one, this is this quantity minus minus, and the last is this one. So, I got this quantity. Now, so from here I will just write that this quantity, whatever the quantity I am writing, so that I will write a factor j, that is a function of u and v. If you see, it is a function of u and v plus this integral, whatever the integral we just got it to a naught v dash this a to v u dx. So, this factor that is written here, so this factor is called, it has a name, special name, and that is called linear concomitant. Why it is called the bilinear? Because it is a linear in the function in the form of u and v. So, this is called the bilinear concomitant. So, from here if you see, then this quantity if I just write, so I can write this as a g of u v plus alpha beta, then I taking the quantity together. So, this will be a naught v double dash plus 2 a naught dash minus a1 v dash. So, for I am taking this quantity and then this and this plus a naught double dash minus a1 dash plus a2 v. So, this quantity I am taking now and then u dx. So, from here what I have done, I have started with v and then lu. So, from here I will get j of u and v plus, and this quantity if you see, this is another a differential operator. So, from here I can write this as alpha beta and I call it some new name is there. So, from here I just write this name. So, I will call it suppose L star of v and then u dx. So, from here, so now it becomes, so from here I can write v of Lu is equal to j of u v plus, and this one, this quantity I can write as a L star v u, this one I can write. So, now this is the quantity we got. Now, the thing is that, so if you see clearly, so from here I have now we are come with the new differential operator and that represented by the L star. Now, what about this quantity? So, let us check this one. So, our j of u v is basically, so this is equal to v a naught u dash plus v a naught u minus v dash a naught u minus v a naught dash u. So, this quantity I am taking. Now, if I substitute the value here, then if you see from here, this u and this u, and I know that the u at alpha and u at beta both are 0. So, from here if I put the limit here for beta and alpha, then you will see that, and this quantity also has a u. So, all this quantity become 0, this is also become 0 and this also become 0. So, we will come up with only v a naught u dash alpha beta. So, this will be v at beta a naught u dash at beta. So, this is beta, sorry, minus v of alpha a naught alpha u dash at alpha. Now, if my concomitant u and v is 0, if I take that this is equal to 0, then if I choose my v beta is equal to 0 and v alpha is equal to 0, from there I will get a new type of condition on the function v, that v alpha is 0 and v beta is also 0. So, if I have this one, so after this one now I can have my v L of u is same as L star v for u. So, by the method of inner product, from here I can say that the L star is an adjoint operator of L. And so, in this case I can say that, and then I also have V alpha is equal to 0 and V beta equal to 0. So, from here I can say that my B star V is equal to 0. So, from here I can say that the B star is an adjoint operator of B. So, this is the boundary adjoint operator B. So, from here now we are come up with the condition that so now what happen if I will find out that my L is equal to L star and B is equal to B star, because if you see here the L star in this case is this one and L was the our differential operator and B was the boundary operator, the 0 boundary condition, and if you see B star, the B star is also the corresponding adjoint operator and they are the same type. So, in that case now if I take if L is equal to L star and B is equal to B star, then in that case we say it is self adjoint system, because in the system we have the operator and the boundary conditions. So, in that case we will say that this system is a self adjoint operator system, and if L is equal to L star and B is not equal to B star, so then we call it as a self adjoint operator. Or I have L is equal to not L star and B is equal to B star. So, in this case we call it self adjoint boundary operator. But in both the cases if you see, then this is non self. Adjoint system. So, it is not a adjoint system. So, by using this one we are able to define the adjoint operator for any linear differential operator. So, let us take one example. So, I will take the example 1, I start with the very simple equation. So, let us take y double dash is equal to some function f x with some initial condition that y at alpha is 0 and y at beta is 0. So, in this case I can say that d square over dx square. So, let us take it u not y. So, this is also u and that is also u. So, del u by del x, del square u by del x square is equal to f x. Now, in this case I want to take, so my L is this one. Now, from here I want to define what is my L star. So, if you see the L star from here, so L star is this, it is depending upon the coefficients of the L. So, L star from here if you see our equation was this one, A naught u double dash plus A1 u dash plus A2 u. So, this was my differential equation. Now, my A naught and A naught is same in this case, but here the coefficient of V dash becomes 2 times A naught, the derivative of this one minus A1 plus the 2 time derivative of A naught minus 1 time derivative of A1 plus A2. It means the coefficient of these are the same. So, from here my L star can be again the same d by dx, and in that case also my B is B and B star both are same, because just now we have seen that V of alpha is also 0 and V of beta is also 0. So, from here if I get these values, then from here I can say that my L is equal to L star and my B is equal to B star. So, these things I can write here. So, I can say from here that this is a self and adjoint system. So, this is the self adjoint system. Now, I go with the another example. So, this is example 2. So, let us take this equation. My L u I am just taking x square u double dash plus u dash plus 2u. So, this is my operator, and then I am applying, this is my boundary condition, u dash 2 plus u 2 is equal to 0. So, this is the boundary condition I am taken. So, in this case I can say that my x belongs to 1 and 2. So, this is my corresponding linear operator. Now, from here I want to find out what will be the L star. So, now I will define this one. So, let us see this one. Now, what I want that there is a function, I choose v and then I take the inner product of this one. So, this one be from 1 to 2 v, and then I will define this one x square u double dash plus u dash plus 2u dx. So, from here I just take 1 to 2. So, I can just take x square v u double dash plus v u dash plus 2 v u, taking the integration. So, again from here I can write down from 1 to 2 x square v u double dash dx plus integration from 1 to 2 v u dash dx plus integration from 1 to 2 times v u dx. Now, the main thing is that I want to solve this one. So, it will be again x square v u dash, taking from integration from 1 to 2 minus 1 to 2. So, taking the derivative of this one. So, it will be, the derivative will be 2x v plus x square v dash. So, this is the derivative taken, u dash dx plus, now from here I am taking again the product rule. So, I will call it v u from 1 to t minus the derivative of v dash u dx from 1 to 2, and the last quantity is as such I will taking. So, 1 to 2 times v u dx. From here, now again I am solving this one. So, this quantity will be same. So, it will be x square v u dash 1 to 2 and this quantity plus v u minus, now this quantity I want to solve. So, if I want to solve this quantity, so this is a 2x v u dash and x square v dash u dash. So, from here I can separately write this one. So, this will be 2xv u dash dx plus 1 to 2 x square v dash u dash dx. So, this is separating, I am doing this one, minus 1 to 2 v dash u dx plus dx. So, I am solving this one now. So, if we solve this one, it will be 2xv u 1 to 2 minus, so this just 2 I am taking outside. So, it will be xv dash u dx. So, this is the corresponding integral, and now if I solve this one, this will be again x square v dash u 1 to 2 minus 1 to 2 x square v dash u dx, and the other quantity will be same. So, if we go further, so from here I can say that if I solve it further, then this quantity x square v u dash plus v u from here minus 2x v u, from here it is coming, and from here it is coming minus x square v dash u. So, this will be my bilinear concomitant, and so this will be my bilinear concomitant plus, so this minus plus will be there. So, then I will get the integration from g 1 to 2, and this will be plus. So, it will be 2 x v dash u from here, and minus sign minus minus plus will be here. So, it will be x square v dash u plus minus v dash u plus 2 v u dx. So, I hope I have made all the calculation right. So, from here, so this is my j of u v plus this quantity. So, I can just expand this one and then solving. So, from here if I just want to write it directly, then it should be of the form x square v double dash plus 4x minus 1 v dash plus 4. This is for u dx, because this quantity will come from here, the x square taking the derivative v double dash plus v dash 2x. So, this will cancel out and it will get this value. Now, the thing is that what is the value of j u v? Now, if you see that here, if I have the boundary condition, my u1 is 0 and u2 is this one. From here I can write that u dash 2 will be minus of u2. So, if you see that here my u1 is 0, u1 is 0, u1 is 0, right. So, from here I can define my j u v. I am just putting the limit. So, if you putting the limit here, it will be 4 v 2 u dash 2 minus 1 v 1 u dash 1. So, this will be the quantity, first quantity, plus V2 U2 minus V1 U1, okay, minus, so this quantity will be there. So, 2 to 4 V2 U2 minus 2 V1 U1. So, this quantity is there minus 4 V dash 2 U2 minus V dash 1 U1. So, that is my given quantity. So, from here if you see, then my this quantity will be 0, this quantity will be 0, this quantity will be 0. So, we are left with only for V2 U dash 2 minus V1 U dash 1 plus V2 U2. So, this is 0 minus 4 V2 U2, this is 0 minus 4 V dash 2 and U2. So, this is the quantity we are getting, and now I also have that U dash 2 is equal to minus U2. So, if I put this value here, so from here I will get, so U dash 2 is here only, this one, right. So, I will get from here, so it will be minus 4 V2 U2 minus V1 U dash 1, then plus V2 U2 minus 4 V2 U2 minus 4. So, this minus V dash 2 U2. So, this quantity will remaining, and from here, so V2 U2, V2 U2, V2 U2. So, it will be minus minus, so minus 7 V2 U2, and then V2 U2. So, this quantity will be there minus V1 U dash 1 minus 4 V dash 2 U2. So, from here if I want my j u v equal to 0, so from here what I choose is that I choose V1 is equal to 0. So, this quantity will be 0, and then from here I want my minus 7 V2 U2 minus 4 V dash 2 U2 is equal to 0. So, from here I will get minus 7 V2 minus 4 V dash 2 is equal to 0, because U2 I do not want to be 0, U2 I do not know about the U2. So, from here I will get this value, and from here I will get the condition that 4 V dash 2 plus 7 V2 equal to 0. So, this is another boundary condition I got. So, from here I will get my VLU is equal to L star VU, right, and that L star. So, now my L star V in this case is so it is x square v double dash plus 4x minus 1 v dash plus 4v. So, that is this one, and I get the boundary condition that my v1 is 0 and 4 v dash 2 plus 7 v2 equal to 0. So, this is my corresponding adjoint system, and in that case you can see from here that my L star is not equal to L, also my B star is not equal to B. So, in this case I can say that this is not a self adjoint system. So, in this lecture we have discussed the concept of the adjoint, that how we can define the transpose of the matrix and then extended that concept to the functional space, and then we define the adjoint operator for the linear differential operator. So, in the next class we will go further and we will try to find out the relation between the Green's functions of the linear operator and its adjoint. Thank you very much for watching.